Hi everyone. Can you hear me? Okay. Yeah. So Sam just talked about the dark hardware world, and the different thing I'm doing is he will focus on the arithmetic abstractions, and I focus on a little bit higher level. So imagine like people try to build beyond a multiplier. Imagine what if I want to build a video decoder? How can I use eGraph to optimize that? So today I'm going to share our recent work here as a tool flow that orchestrate using eGraph to try to orchestrate hardware optimizations to do some algorithm-aware optimizations. So so the hardware design is hard, as Sam said. So the software and hardware speak completely different languages, and so it's really hard to connect them. And in practice, it takes a lot of human intervention to jump between software and hardware abstractions to map a software algorithm into a custom hardware. So to solve this, fortunately, we got a new technique called high-level synthesis, which is a process that automatically translates a software program or specification into a hardware circuit. So this allows a software engineer without hardware background to customize their own hardware designs. So this is nice, isn't it? But this is not really the case in the real world today, because one of the most reasons is because existing software program can be really scary because they were not written for hardware designs. So this is my favorite example of C code called Dove device. It's an efficient rewrite of loop unrolling for CPUs by Tom Duff in 1983. But if we look at the code, it's super scary for most compilers because the code has switch statement and a while loop that interleave each other. So this cannot really be interpreted very well by existing tools. So in reality, we need huge efforts to rewrite such program so that tools can well interpret that structure and for potential other optimizations such as hardware optimizations. So here is how actually the HRS development flow works. We start with software specifications or existing software programs downloaded from any libraries. And then we need a lot of rewrites to make the source into a HRS-friendly code. So this involves a lot of like loop transformations, including like loop unrolling, loop flattening, perfection on loop fusion. Particularly like loop flattening is like converting a nest loop into a single loop. And loop perfection is basically moving the loop bodies of all the in the loop nest into the innermost loop. And we also interested in if conversion, so that remove the control path of the source by inlining all the if statement and else statement into the code body, so that will form into a mux in data path. And the memory forwarding is basically remove redundant memory access in the source that cannot will not affect the results. So that will provide a simpler memory dependence graph for the compilers. So second, apart from the source, the hardware design also involved a lot of design constraints that to explore the design quality of the hardware at a different aspects. So particularly like we can explore like more hardware optimizations such as like the loop unrolling factor and the pipelining depth, try to explore the trade-off between performance, area, and power at different for different use cases. And this is also well known as a design space exploration process. So basically, a user specified a design space based on the design constraint the tool wanted to explore, and there is a script like automatically try to find the most efficient combination of these design constraints. And with this design constraints, an HRS tool like then automatically generates an hardware based on this specification. And this involves scheduling that maps an untimed like C program into clock cycles. So and also like we have bindings that try to share the resources of hardware operators without affect the performance or with minimal effect on the performance. And retiming is trying to minimize the clock period of the hardware. Certain HRS tools also do verification that try to prove to ensure the equivalence between the output hardware and the input software for correctness. And then we have the EDA tools to take the output Verilog code and then generates proper like chips or a netlist on FPGA. So this is basically the HRS design flow. Fortunately, HRS tools and the Sims tools are already fully automated, and design space exploration can also be semi-automated as long as the user provided design constraints to explore. Unfortunately, the HRS tools cannot really handle the rewrite very well, mostly because the software program can be any form, as I presented before. So this is the interest that we try to dive into in this talk. Like, can we actually do an automated rewrite for HRS code? And we know, like, finding an optimal design is like finding a way out of a maze. Particularly, like, both style of the transformations and its order being applied will affect the quality of the final outputs. And this is more complicated in the HRS world because we also have software source level software optimizations, and then also hardware optimizations at the different abstractions. And this forms a multi-level phase ordering problem. So can we actually explore this in an efficient way? Like, can I explore them in parallel? Or can I explore them in a way that I can remember the path that I explored, so I can not just coming back from the starting point, but like in an intermediate point to reuse my results. So this is the motivation that's why we want to use eGraph to efficiently explore all this design space. So we propose SEER, and here is an overview of SEER. So SEER stands for Super Optimization Explorer using eGraph rewriting. So the first problem we had is the software program and eGraph do not speak the same language as well. So here we implement our own intermediate representation named SEERLAN, try to connect this existing eGraph structures with software programs. So particularly, SEERLAN connects with MIR, which is a part of the LVM and is the state-of-the-art compiler framework. So the reason is mostly because MIR already contain a wide range of compiler parsers that we can orchestrate to explore directly in SEER. And also, like MIR opens opportunities, like we're just not taking C or C++ code or this language. We can take any software programs as long as they can be lowered into MIR. So, and then we use traditional like eGraph exploration mechanisms, such as tools like in a such as egg. So, and then we can orchestrate existing external tools, try to do all the kind of explorations within SEER. So here we use a MIR process for software level source transformations, and also Intel Rover is a hardware optimizer implemented based on egg. So next, I'm gonna take MIR for example. So this code, this is a code example contains 3 sequential loops. Both the first and the last loops have inter-iteration dependence on the array X. So an inter-iteration dependence means that the start time of an operation in an iteration depends on the end time of another operation in the previous iteration. So the first and the last loops cannot be fused because they have inter-iteration dependence. Then we only have 2 choices of the loop, to fuse the loop. We can either fuse the first loop, so F and G are executing in parallel, or we can fuse the last 2 loops, so G and H are executing parallel. And it's not really clear which one is better, because this transformation is only beneficial, whether it's beneficial is depending on the external code that calls this representation. And we don't know anything about external code at the moment because they might be changed in a later optimization stage. So we cannot really make a proper decision at this moment. So a good idea is like we can keep both of them in the eGraph. So let me show you how we do that. So here is a simplified SEERLAN of this code. So seek indicate the execution order of these loops. And then we have AST like that, putting that in the eGraph. So SEER construct initial eGraph, and then we try to implement loop fusion rules using interface with MIR transformations. So each rewrite rule is implemented as a dynamic rewrite with a condition whether it's successful or not. So for example, in this case, we got a loop fusion matched with two sequential loops, and whether we can fuse them into a single loop based on the condition of MIR path. So for this example on the left, we grabbed loop 1 and loop 2 are actually sequential. So the idea is like we wanted to translate this particular representation of the program like back to MIR and ask the MIR loop fusion path to see, hey, could you fuse them? And if that is successful, basically by checking the difference between these two programs, if that's successful, we will convert that back to a CRLAN representation, and then we can just union back to the EGRAPH. Then we have a new representation in the EGRAPH, and that would allow us to explore everything in the same time. And this is not just loop fusion. So there are a variety of programs, program transformations carried out in the compilers. So there are typical 3 groups of transformations at different abstractions. The first one is control flow level transformations, which change the control flow graph of the original program. Particularly in this work, we target transformations for for loops and if statements. The second group is the data path level, which is Sam's work mostly focused on. So that includes expression balancing and operation reduction, things like that. Even the lower abstraction is the logic gate level, is where logic synthesis tools is interested, is try to play with gates and achieve a smaller circuit. So in such a huge design space, we hope the user just needs to provide input program and the rewrite rules they want to explore. So Seer can automatically explore them, try to find an efficient design that meets all their requirements. There is a small verification story here. So how do we make sure that all these transformations is correct? This is probably like an interesting thing in software, because most hardware transformations are already formally verified. But in the software community, like existing software compiler passes are often unverified. Imagine like we just download a LVM pass and whether it works, I don't know, right? So it could be errors in traditional compiler passes. And this is actually fine in software design world, but we can't just afford like try again, because that takes years to validate and cost multi-billion like dollars. So here for each transformation, we translate the CRLAN back to system C code and then ask a commercial equivalence checker to verify the equivalence between these two representations. So that will ensure the correctness of our design. Okay, so now Seer explores these transformations, and we got a huge EGRAPH in hand. So and then we apply like program analysis at a source level and estimate the hardware resource and the hardware resource and powers based on some heuristics, and then we evaluate each representation in the EGRAPH and try to extract the most efficient representation that for HRS tool to generate the hardware. And basically in this, for this work, we just set the maximum performance and the minimal area. So hopefully we can get a smaller and a faster chip. Over a set of benchmarks, we actually achieve quite good results compared to directly sending the program into HRS tools. We achieved like 3.1 speed up, and with a little overhead because faster means slightly bigger. But the power is a bit higher, mostly because the high performance. But it kind of makes sense because it's not in the cost function, so that's why it's out of control. All right, so so far we've seen a working flow, and the lesson we have learned is it works, and using existing tools seems efficient, but it's not exciting, right? So now I'm going to show you something interesting that we actually observed while we're developing Seer. It's quite interesting. So we find that the Seer can improve analysis capability of existing analyzers without changing it. So here is another example of 3 loops, but it's slightly different from the previous one. So both the first and last loop have read and write access to the same array X. One array index is 3 times the loop iterator I, and the other one is I shift left to 1 plus I. So as a human, we know these 2 expressions are equivalent, but the software compilers are struggling to find out. Traditional compiler analyzes memory dependencies using affine memory access. An affine expression is a constant times the loop iterator plus a constant. So then the analyzer cannot determine whether there is a memory dependence across the iteration in a loop because they can't figure out the shift and add operations as a memory index expression. And conservatively, they assume there might be a memory dependence between the first loop and the last loop. So the tool says, I can't fuse them. Then we come back to the same thing, like we can either fuse the first two loops or the last two loops. Based on the objective function where we specified that the tool decided to fuse the last two loops. And we still got some, because the loop fusion is beneficial, so we still got some speed ups. But as a human, we are not happy because we know everything can be fused. So, so this means like we wanted the tool to know that there is absence of memory dependence. So interestingly, with the EGRAPH we can obtain the program invariance from one representation and pass it to another. During the exploration, we apply some arithmetic rewrites on the original program. So then we can turn this shift and add operators back to the multiplier. And then we got a version that all the memory accesses are in affine form. So with this program representation, the static analyzer can easily identify, oh, there is no memory dependence between the three loops, and we are happy to fuse them. And then we can even apply more like software optimizations in the loop body to simplify the code, such as common sub-expression elimination. So we got a smaller loop body. And then for hardware designs, so shift is free and adder is cheaper than a multiplier. So now we want to get efficient hardware. So we wanted the shift and adder back. So in this case, we apply the arithmetic optimization again, got a hardware-friendly expression at the end. So finally, we got a better performance and lower power than compared to just fusing two loops. So this is an interesting example that we explored, and it's quite complicated. So I just quickly mention that. So this is like two hardware experts spent like one afternoon to try to optimize this code. And we also try to use SEER, try to see how far we can go. So that involves like 6 different niche optimizations. In order to get there, it has to be applied in a fixed order. So, and we try to compare that with SEER. So we put this, so basically we did 2 things. We put this program into SEER to see what happens. And we also put the manually optimized code into SEER to see what happens. So this is mostly in the SEER and the SEER manual. And we can see we can further optimize. We achieve a better performance compared to the manually optimized the code. There is a slight difference between the 2 SEER outputs. That's mostly because we only got a finite number of transformations. That's it's not the same set as the manual optimization did. But we also compare a set of benchmarks that with manual optimizations with HRS tools, and we still got like basically for 45% speed up. All right, so this is actually exciting because EGRAPHS could help experts to improve their designs. So because this is our first attempt at applying EGRAPHS at a high-level synthesis, there are a variety of future directions that we want to explore. And this includes like languages, optimizations, and verifications. So here the CRLN is implemented as a translation medium between MIR and EGRAPH. So in the future, we wanted to do a deeper integration of CRLN into try to identify the most efficient boundary between MIR and EGRAPHs. And also scalability is one of the most important thing. So because we apply dynamic rewrites, it might be not an efficient way of to connect the MIR and the EGRAPH. So there might be a better way to do extraction and exploration. And finally, the verification bit is a bit painful because every time we have to translate the CRLN back to system C for verification. So it would be nice if we integrate that into a deeper integration that we only compare 2 the changed bits between two CLNs instead of try to verify the equivalence of the whole program. Cool. Thanks. If you find this interesting, feel free to come to me after talk. Thanks.
We have time for a few questions.
Thank you for a great talk. I wonder if you also consider critical paths in optimizing the circuit, and also it is related to the first question. Do you consider some dynamic scheduling for the generative circuits? Thank you.
Thanks. That's a good question. So at the moment, we do not handle like retiming because we rely on the HRS tool to do that. This is one of the benefits, one of the main benefits. But that's why doing HRS tools, because they can automatically do retiming. But I think Sam is working on part of the try to integrate retiming into the EGRAPH. So we might. I think it's possible, but we don't know how to do that in HRS at the moment. Yeah, because it mostly because it generates HRS code rather than the timed and Verilog code. For the second question, dynamic scheduling is, well, my PhD mostly working on dynamic scheduling, so so this one is more static scheduling based. It's definitely interesting future direction, yeah. But we haven't do anything about that yet. Yeah, thanks.
Do you think there's an interesting interaction between MLIR being dialect based, and hence you've got lots of different program representations of the same thing, and the EGRAPH?
Yeah, so this is part of the future works. I think this is one of the within the future directions of deeper language integration. So I think there are different design choices about how we deal with MIR within an interface with EGRAPH. I think one of the main interesting is how do we handle different dialects in EGRAPH, or should we have a dialect about EGRAPH in MIR? So I don't know the answer yet, but I think both directions are interesting.
Okay, let's thank the speaker one more time.
Thanks.